So in this lecture, we're going to be following up on covalent compounds. So covalent compounds is not as straightforward as I have presented it to be initially. There are actually two types of covalent compounds. We actually have polar covalent compounds and we have non-polar covalent compounds. So deciding whether a covalent compound is polar or non-polar for binary, which means there's only two atoms present, covalent compounds, is actually quite easy. And again, the key to this whole polarity of covalent compounds is page 3 of your exam reference sheet, okay? So if you have the molecule hydrochloric acid or hydrogen chloride, the electronegativity from the table for hydrogen is 2.1 and the electronegativity for chlorine is 3.0. So what we do is we subtract them from each other, and whatever number you get, doesn't matter whether it's negative. You need to have the absolute value, so that turns positive anyway. The electronegativity difference, or delta En, is actually 0.9. And any delta En from 0.5 to 1.7 is actually considered to be polar covalent. So therefore, in this case, hydrochloric acid or hydrogen chloride is actually a polar covalent compound. Okay? Polar compounds have special notations. Okay, so what happens is whichever atom that has the higher electronegativity, in this case chlorine, actually has the delta negative size symbol, and whichever atom is on the other side of that delta negative symbol must be given a delta positive symbol, like so. Okay? Now, where does this come from? The reason why this region, this is actually called partial negative and partial positive, is because even though polar covalent compounds are sharing electrons, that electron, because chlorine is much more of an electron lover than hydrogen, is actually going to reside around chlorine more times than around hydrogen. Now recall that electrons are negative. So if something negative is around you more often, what happens to you? You become partial negative. If something negative is away from you more often, what happens to you? You become partial positive. And that's why we have this big clouds. This big cloud basically just tells you that this one has more electrons most of the time, again, because that electron being shared is actually more on chlorine side rather than hydrogen side. There's also a arrow that's always drawn towards the more electronegative element, and that's actually called dipole moment. Dipole meaning two poles. Something positive is one pole and something negative is the other pole. If another example, so in this case, so that's an example of a polar covalent compound. What happens when you have boron monohydride in this case? Boron has an electronegativity of 2.0. Hydrogen has an electronegativity of 2.1. The electronegativity difference is 0.1. That's less than 0.5. Therefore, this is nonpolar. The good thing about nonpolar molecules is we do not have to draw partial negative, partial positive charges and indicating dipole moments. Okay? So again, binary covalent compounds, identifying something polar and nonpolar is quite simple. What happens, however, when you have ternary or higher covalent compounds, meaning to say you have 3 or more atoms? Maybe what I should do is I should just do an example. Okay, so I am gonna do in this case carbon dioxide, okay, CO2. So carbon dioxide in Lewis structure looks like this. So you have 2 oxygens, which has 6 valence electrons, 1 carbon which has 4 valence electrons. There's no charges, meaning to say there's no extra or less electrons. Okay, so the full complement. So again, the first chart is we bond 1 electron each first and check to see if the octet has been met. If we single bond oxygen went from 6 to 7. This action also goes from 6 to 7. This carbon goes from 4 to 6 because now it has 2 bonding electrons. So as we can see, the octet is not satisfied with both of this, okay, with either one of these atoms, carbon or oxygen. So what happens? So again, if a single bond cannot meet the octet rule, what do? We go to double bonds. Okay, so we just move electrons closer to each other. And what happens? Voila. Oops. You actually have met the octet rule. So in this case, this is how carbon dioxide looks like. So if you look at your table of electronegativity from page 3, we know that carbon has an electronegativity of 2.5. Okay, and oxygen we know has an electronegativity of 3.5. Right? Meaning to say that oxygen is more electronegative than carbon. So what we're going to do is we're going to draw those symbols that we had drawn before. So we're going to put partial negative on both. Okay. And we're going to draw a partial positive on carbon. Okay. And again, recall that dipole moments always goes towards the more electronegative element. So I'm going to draw one on that side. I'm going to draw one going on the other side here as well. So there is a dipole moment. The bonds between carbon and oxygen is actually polar. However, weirdly enough, this molecule, folks, is nonpolar, regardless of this difference in electronegativity. Now, if you look at this, the difference in electronegativity is quite huge. It's 1. However, this molecule is not polar. Why is that? Well, if you look at it, the flow of electrons from carbon to oxygen goes from this carbon to that oxygen, but is also occurring simultaneously to the other side. And if we think about forces, okay, vectors, whether physics or not, what happens is if someone's pulling you this way, but someone else is pulling you the opposite way, and if they are exerting the same force at you, guess what? The electrons, in this case, do not move at all. So in this case, the electrons actually do not go to this oxygen, these electrons actually do not go to the oxygen, because both of them are pulling equally in opposite sides of this low electronegative atom. What happens is there is actually no dipole moment. This dipole moment, if you stack it on top of each other, actually cancels each other out. That is why this is actually a nonpolar molecule. So geometry makes a big difference, makes a big impact about polarity in this case. Okay. Now there are some shortcuts like that you can actually do when it comes to ternary compounds. And again, the key to this one is knowing how to draw Lewis structures. Okay. Example is water, right? So water we know is H2O, right? In this case, I lied. Hydrogen is not in the middle. Oxygen is in the middle. And what happens is you have 1, 2, 3, 4, 5, 6 again. 2 hydrogens, all right, bonded together. What happens, folks, is this is actually a polar molecule. Water is a polar molecule. And the reason why this is, okay, is if you look at it, because the central atom has lone pairs. Lone pairs means pairs of electrons that are not bonded to any other atoms. Okay, these are bonding pairs, these are non-bonding pairs. As you can see, there's 2. As soon as you have a lone pair, 1, 2, 3, however many, in the central atom, we are going to generalize in this class that that molecule is going to be a polar covalent compound. Okay, but again, this comes from knowing how to draw Lewis structures, and knowing how to draw Lewis structures comes from knowing valence electrons. Okay, so geometry in this case is actually quite important in deciding whether something is polar or not. Okay, so in sum, for this lecture, know that there are 2 types of covalent compounds: polar covalent compounds and non-polar covalent compounds. There's actually a shortcut. So we know that water is a polar covalent compound. Liquids that dissolve in water are actually polar as well. Okay, liquids that do dissolve in water are actually nonpolar. Okay, solids that dissolve in water are possibly polar or ionic, but solids that do not dissolve in water are perhaps more than likely going to be nonpolar. Okay, oil, folks, is a nonpolar compound. Okay, so anything that dissolves in a nonpolar compound is actually also going to be a nonpolar compound. So that's actually one of the key ways that you can actually decide whether something is polar or nonpolar. The other thing is the state of matter. Anything that's gas at room temperature is generally going to be a nonpolar compound. Okay? Now, if it's liquid at room temperature, all bets are off because that could actually be a polar or nonpolar compound. All right?